Hello and welcome to the logic of it all. This is our second video on finite state transducers. Let's start by a quick review of transition diagrams. So in the previous video, we talked about how a finite state transducer can be represented using a directed graph that we call the transition diagram. Now, if you look at this example, first of all, the nodes or the vertices of this directed graph represents the state of the machine. So we have two states here, namely S0 and S1. So we have two states. And then the edges represent the transition. So for example, if you look at this edge here, what this edge tells us is if we are at a state S0, if our current state is S0, and our input symbol is a 0, then we need to transition to S1 and output a 1. And similarly for the other edges. So each edge is labeled with something like this, where the symbol on the left side of the arrow is the input symbol, and then the symbol on the right side tells us what the machine outputs in that situation. So for example, if you focus on this edge here, what it tells us is if the current state is S0 and the current input symbol is 1, then the output symbol is going to be a 1 and the machine stays at S0. And then the other two edges, let's quickly review those as well. So this edge down here, what it tells us is if our current state is S1 and we read a 0, we output a 0 and transition back to S0. And finally, this edge here, what it tells us is if the current state is S1 and we read a 1, we output a 1 and we stay at S1. So this is called the transition diagram for a finite state transducer. Now, what we are going to talk about first in this video is the same information about a finite state transducer can be represented in two tables, namely a state transition table and an output table. So instead of the diagram, we can provide the same information about the machine through these two tables. So the state transition table, what it tells us is, given the current state and the current input symbol, the table tells us where we need to transition to. So it tells us what is the next state. Okay, so given a pair of state and input, it tells us what the next state is. So that's called the state transition table. And then the output table, given the same information, namely the current input symbol and the current state, it tells us what the machine outputs, what the output symbol will be. Now, through the next two slides, I will show you how this works through two examples. So here's our first example. So you see this finite state transducer with three states and all the transitions. Now, if you study this graph, this is the behavior that is going to be important for the state transition table. So for example, if we are at state S0 and our input symbol is a 0, the machine outputs a 1 and transitions to S1. So the output doesn't matter in this case because we are interested in the state transition table only. So one more time, if we are at S0 and we read a 0, we move to S1. On the other hand, if we are at S0 and we read a 1, we transition to S2. And then if we are at S1 and we read a 0, we transition to S0. And if we are at S1 and we read a 1, we transition to S2. And finally for S2, if we read a 0, we transition to S0. And if we read a 1, we stay at S2. So that's the information about the transition. So note that I didn't focus on the output because the transition table does not contain that information. For that, we create a separate table called the output table. So all of that can be summarized here in this table. So you see, if the current symbol is a 0 and we are at S0, we go to S1. If the current symbol is a 0 and we are at S1, we go to S0, and so on and so forth. So it covers all the 6 possible transitions. Now, for the output table, we don't include the transition information, and we only include the output symbol. So given what the current state is and what the current input symbol is, we want to know what the output symbol will be. So for example, if the current state is S0 and the input symbol is a 0, then the output is a 1. If the current state is S0 and the input symbol is a 0, or not that, the input is a 1, sorry, then the output is going to be a 1 because of this edge, and so on and so forth. And all of this can be summarized in a table that we call the output table of our finite state transducer. So for example, on input symbol 0, if you are at S0, your output is going to be a 1. If your input symbol is a 0 and your current state is S1, your output is going to be a 0. And if your current input symbol is a 0 and you are at S2, the machine is going to output a 1, and similarly for the second row of the table. So you see that if we have these two tables, then we don't need the diagram, and because the two tables together represent the same information about the finite state transducer. Now, here's a formal definition, like the mathematical definition of a finite state transducer. So to give the full description of a finite state transducer, these are the bits of information that we need to provide. So it's a 6-tuple S, S0, I, O, next, and out. Now, what these names represent, one by one, S is the set of all possible states. So if you have like 2 states, S0, S1, if you have 5 states and so on, so you need to provide that information. You need to say how many states exactly your machine has and what are the labels, the names for those states. S0 is the initial state, so we need to specify that because when we are processing an input stream, we need to know which state we need to start from. So that needs to be determined. So that's the second part of the definition of a finite state transducer. So we need to specify which state is the initial state of the machine. I is our input alphabet. Now, in the previous examples, our input alphabet was 0, 1, but it could be many other things. And then the next one is the output alphabet. So we need to provide this information, what output symbols the machine uses. It could be, again, 0, 1 binary, or it could be like in the previous examples, we saw one where the output symbol is either an A or a B. It could be all the letters in the alphabet and so on. So we need to provide that information when we are introducing a finite state transducer. And now the next two are similar to the tables. So next is a function that takes a pair of input versus state, current state, and it tells us what the next state is going to be. So for example, if for your input symbol is 1 and then you are at S0, then next can tell you to go to S2. And then if your input is 0 and your current state is S0, next can tell you to go to S1, and so on and so forth. So that's what this function next does. You provide the current input symbol and current state, and it tells you what the next state is going to be. So as I said, similar to the state transition table. And as you can guess, the last one, out, is similar to the output table. So it's a function that takes 2 inputs, namely the current input symbol that comes from I, and the current state comes from S, and based on those two, it tells you what the output symbol is going to be. So it gives you an element of O. Remember, O is the set of all output symbols. So it could be that it tells you if the input is 0 and you are at S1, then you need to output an A. If you are at S2 and your input is a 0, you need to output a B, and so on and so forth. So that's what this function out does, which is similar to the output table that we introduced in the previous slide. So overall, this is the mathematical definition of a finite state transducer. So you need to provide 6 pieces of information. One more time, the set of all states, what is your initial state, what are your input symbols, what are your output symbols, how the state transition works through this example, and how the output works through the last piece, which is the out function. Now, the rest of this video is going to be about still finite state transducers, but from a different point of view. So far, we provided the finite state machine, and the question was analyzing the machine. So for example, given an input stream, what would be the output stream, and so on. But in many applications, what you have is a behavior that you expect from a finite state machine. You want to design a machine that works that way. So we have some problem that we want to solve, and we want to design a finite state machine that behaves exactly as specified. Okay, so that's what these 3 examples are about. Now the first one, the first description of a finite state transducer, says that your machine outputs an A whenever the last 2 symbols read are 0. So if it reads 0, 0 anywhere in the input stream, it outputs an A after reading 2 zeros in a row. And otherwise, it outputs a B. So now what's implicit here is that your input alphabet is 0, 1. Maybe I should have mentioned that explicitly, but it's clear that the output symbol is, so this is the input symbol, input alphabet, and the output alphabet is, it either outputs an A or a B, so that's A, B. Okay, now let's see how we go about designing this finite state machine. So there's always an initial state, so start from that. So let me call that S0 and designate that as the initial state. And now let's think about the behavior. Now, if you are at S0 and you see a 1, okay? Now remember, what this machine is looking for is 2 zeros in a row, right? Because it outputs a B unless it sees 2 zeros in a row and then it outputs an A. So that's the behavior, right? So if we are at S0 and we see a 1, first of all, we should output a B because that's not 2 zeros in a row. That's the first symbol, and the first symbol was a 1. So we should output a B because we haven't seen 2 zeros in a row. And I claim that we need to stay where we are. Now, the reason that we need to do that is because, so on input 1, we output a B and we stay at S0. The reason that we don't transition to a different state is, if you remember in the previous video, we talked about what these states represent. These states represent what the machine needs to remember. So going from one state to a different state means that the machine needs to change its state of memory, which means that it needs to remember something different. Now, in the case of this machine, based on the description or the expected behavior, the only thing that this machine needs to remember is whether the previous symbol that it read is a 0. Because if it was a 0, then we have half of what we are looking for. Remember, we are looking for 2 zeros. So if the last symbol read is a 0, then the machine needs to remember that, because then after that, if it reads another 0, it needs to behave differently. It needs to output an A. So this is what the machine needs to remember. What was the previous symbol that I read? If it's a 0, then it means I'm waiting for the second 0 to create the 0, 0 and then output an A. And if it's not a 0, then I am not remembering anything, because the only thing that I care about is 2 zeros in a row. So because of that, if our current input is a 1, that never leads to 0, 0 by itself. So we don't need to remember that we have seen a 1, because that 1 is irrelevant for creating 2 zeros in a row. That's why we don't change the state, because we don't need to remember that we have read a 1. Okay, and then based on the description, because we have not seen two zeros in a row, we output a B, so that's why we have a B here. Okay, so next step, what if we are at S0, our initial state, and we see a 0 as our input? Now it's a different story because we have read the first half of what we are looking for. So we need to remember that. We need to remember that I have read 1 0, and that means if I read another 0 after that, then it's a 0 0. So how do I remember that is by changing my state. So if I see a 0, I change and go to another state. Let's call that S1. And what should I output in this case is still a B because I haven't seen two zeros in a row. Right? Remember, the only case that our machine outputs an A is if the last two symbols are zeros. But here we only have 1 0 and we haven't seen the second one. So now we are at S1. Okay. Now the transition from S0 are complete because it's either that the input is a 1 or a 0, and we have covered both of them. Now to finish this up, we need to talk about the transitions when we are at S1. So what happens when we are at S1 and we read a 0 versus what happens when we are at S1 and we read a 1. Okay, so here we go. We are at S0, which means that we have read 1 0. The last symbol that we have read is a 0. Now, if we read a 1, let's start with that. So we have read a 0. So the last symbol that we have read is a 0. Before that, we don't know or we don't care. The last symbol that we have read is a 0. That's why we are here at S1. And now we are waiting for the second 0 to output an A. But what if we see a 1 instead of a 0, a second 0? So first of all, because again we have not seen two zeros in a row, we need to output a B. And this 1 here destroys the pattern of seeing two zeros. So now this 0 is irrelevant. We don't need to remember that because remembering that meant the last symbol that I've seen is a 0. I'm waiting for the second one. But with this 1, we need to start over. So it means that we need to go back to S0. And so if we see a 1, we go back to S0 and we output still a B because what we have seen is 0, 1, not two zeros. And one more time, the reason that we go back is because now we need to see two zeros again, because this 0 is not useful anymore, because now the last symbol is a 1. So the only way that we can output an A is if there are two zeros. So that means start over, go back to S0. And finally, if we are at S1 and the symbol that we see, the next symbol is a 0, that's going to be the second 0 because we have seen a 0 and now the second one. So we output an A finally, and we stay where we are. Because we are still, the last symbol that we have seen is a 0. So we have seen two zeros now. And we stay at S1 because if I see another 0, that's still two zeros in a row, so I need to output an A again, and so on. Now, one thing that might help in designing these besides practice is naming these states in a better way. So another way that we can, instead of calling them S0 and S1, I can say S0 is the state where the last symbol read is not a 0. Okay, and S1 is the state where the last symbol read was a 0. Okay, so if we are here, it means that the last symbol that we have read is not a 0. And so for example, if we see a 1, that's not a 0, so we need to stay here. But if we read a 0, now the last symbol that we have read is a 0, so we need to go to this state. And when we are here, if we read a 0, we stay because still the last symbol that we have read is a 0. But if we see a 1, now the last symbol that we have read is not a 0, so we go back to S0. So sometimes giving them more descriptive names can help in understanding why the design looks like that. And here's a cleaner version of that same machine. Okay, next example. Along the same lines, we want to design a finite state transducer, and the behavior that we expect is whenever the machine sees two zeros followed by a 1, it outputs an A, and otherwise it outputs a B. So in the previous example, the pattern that the machine was supposed to detect was 0, 0. So whenever it sees 0, 0, it outputs an A, otherwise it outputs a B. Now the pattern here is a little bit more interesting. The pattern that the machine looks for is two zeros in a row followed by a 1. So it looks for this in the input stream, 0, 0, 1. So whenever in the input stream it sees 0, 0, 1, it outputs an A, otherwise it outputs a B. So that's the machine that we want to design. Now I go a little bit faster because this is somehow similar to the previous one, obviously a little bit more involved because the pattern is a little bit more interesting and more complex. So this is our initial state. Now the states that we need here is we need to know whether we have seen just one zero, or we have seen two zeros and we are waiting for a 1, or we have seen the entire 0, 0, 1. Okay, so starting from S0, if the first symbol is a 1, that doesn't help me progress in creating 0, 0, 1. So with a 1, I stay here. And since I haven't seen the pattern 0, 0, 1, I am supposed to output a B. I output an A only when I see 0, 0, 1. Now, if I am at S0 and I see a 0, that's improvement. That's progress towards 0, 0, 1. So I need to remember that by going to another state, S1. But again, remember that this is progress, but I'm still waiting for the second 0 and the 1. So I haven't seen the full pattern. So I still output a B. Now, while I'm here at S1, if I see another 0, that again is progress because I've seen the first 0, that's what brought me here. Now I see another 0, that means two zeros in a row. So I need to move on to a different state, let's call that S2, where in the state S2, it means that I have seen two zeros, two of the zeros, and I'm waiting for a 1 to finish the pattern. But still, I haven't seen the entire thing, so I output a B. Now, on the other hand, if I am at S1, which means I have seen a 0, and the second symbol instead of a 0 is a 1, that kind of breaks the pattern because I have seen a 0 here. So the first symbol that I read is a 0. Then I see a 1, and that doesn't help me see 0, 0, 1 anymore. I have to start over. So starting over means transitioning back here. So with a 1, I transition back to the state, the initial state, which means I start over. And that's not the pattern that I'm looking for, which is 0, 0, 1. So I output a B. Now I need two more transitions from S2. If we are at S2, and which means what? Which means if you are at S2, it means that the last two symbols that we have read are both zeros through this arrow and this arrow. That's how you get to S2. So I have seen 0, 0, and I'm waiting for the final 1 to finish the pattern. But if I see a 0 instead, then that doesn't give me what I'm looking for, 0, 0, 1, but I'm still seeing two zeros as the last symbol and waiting for a 1, which means that I'm still here. So with a 0, that doesn't give me the 0, 0, 1, so I output a B, but the stay put, waiting for that 1 to give me the full pattern. And if I am at S2, which means that I have seen the two zeros, waiting for the 1, and I see the 1, then obviously that's the full pattern and I need to output an A. But where should I go? So when I see that 1, that finishes the pattern 0, 0, 1, but then it means that I have to start over for the next 0, 0, 1. And starting over means I need to go back to the initial state. So that's what happens when I see a 1. That's A, which means that I have seen the pattern 0, 0, 1. And then I go back to S0 to wait for the next 0, 0, 1. So that's the finite state machine that that satisfies the specification. And here's a cleaner version of that.